Dear audience, good morning. I have the pleasure today to present my research work during this first national online conference in materials physics. The title of my presentation is Structural and Electronic Properties of the Perovskite Strontium Chromates DFT Study, under the theme of Simulation of the Physical Properties of Materials. My name is Ouahiba Ramdane, under the supervision of Professor Salim Al-Abidi. My presentation outline will be as follows. Firstly, I'll mention the computational details, then results and discussion, where I will present the structural and the electronic properties of this perovskite. Finally, I will end up the presentation with conclusion. The cubic PM3M with space group number 221 geometry of the crystal structure for strontium chromate perovskite was considered with the experimental lattice parameter equal to 3.82 angstrom. The full potential linearized augmented plane wave FPLAPW method was used for the geometry optimizations and electronic structure calculations by using the Win2K code. The tetrahedral method and the complete Brillouin zone with 1000 kJ points was used for integration. The expansion of wave function was carried out by taking the plane wave expansion cutoff RMT max equal to 8.0, where RMT is the atomic sphere radius and the Kmax is the plane wave cutoff. The exchange correlation energy was treated by the generalized gradient approximation GGA08 with cutoff energy equal to -6 Rydberg, which defines the separation of valence and core states, and energy convergence criterion set to 0.001 Rydberg. Now I will move to the obtained results. The structural properties of this material can be theoretically calculated by its volume optimizations process. So, to investigate the stable state of strontium chromate perovskite, both the ferromagnetic and the non-magnetic states have been examined. After the optimization, we obtain the total energy as a function of the unit cell volume for the two states as shown in this figure. The results here confirm that the stable state of this perovskite is the ferromagnetic state. The optimized lattice parameters, in addition to the parameters and the total energy from Marnagin's equation of state, are summarized in this table. As we can see, the computed values are in good agreement with the experimental results and other theoretical calculations. In this slide, I will present the electronic properties. The optimized lattice constant of the ferromagnetic state, stable state, was utilized to calculate the electronic properties. To determine the electronic band structure of strontium chromates, the two bands have been computed in high symmetry directions of the first Brillouin zone as shown in this figure. Here, the Fermi level is illustrated by a horizontal line and set to 0 electron volts. And it's so clear from spin-resolved bands plots that the GA approximation designates this material as a metal, due to the presence of some bands at the Fermi level for both spin configurations up and down. Now, in order to confirm this result, we studied the total and the partial density of a state for strontium chromates. For the total density of a state, as shown in figure on the right, it can be seen that there is no symmetry between spin-up and spin-down configurations. This designates that the system shows a magnetic behavior. Also, we confirm the metallic behavior of this material by the presence of some dose at the Fermi level. However, for the partial density of a state, it can be clearly seen that the chromate d electrons play a significant role in predicting the electronic properties of this material. Conclusion: DFT-based calculations using GGA have been performed to investigate the structural and the electronic properties of the strontium chromates perovskite. The calculated equilibrium lattice parameter is found in good agreement with previous experimental and theoretical results reported in the literature. The stable state for strontium chromates is the ferromagnetic order. And finally, the GGA approximation improves the metallic behavior of this material. Thanks for your attention.